for BaSSL, boundary-aware self-supervised learning for videos in segmentation. My name is Jong-an Moon, and I'm working in Kakao Brain. In this work, we tackle video scene segmentation task, which aims to temporarily localize scene boundaries given an input long video such as movies. While there exists a task of identifying sharp boundaries for a scene, however, we focus on scene boundary detection because the scenes are semantic unit for making a story, thus it is more important to understand long videos. The task is typically formulated as short-level binary classification with a slide window scheme. Given a video divided into a series of shots, each shot is classified as boundary or non-boundary ones. In practice, rather than taking a single shot, a window including preceding and succeeding neighbor shots is leveraged to exploit contextual information for precise decisions. It is fed into the shot encoder, followed by the contextual relation network. The shot encoder is responsible to capture the spatial temporal patterns of individual shots. The contextual relation network is in charge of capturing the relations between shots, such as coherence and difference. Then, it is determined whether the given shot is a boundary or non-boundary one, and in a supervised manner. However, annotations from long videos are extremely expensive, so the scene segmentation is limited by the small scale of the dataset. Therefore, in this work, we tackle the task by self-supervised learning to boost the performance. With this formulation, we can take the advantage of in-domain representation learning with a larger number of videos without expensive labels during the pre-training stage. And we can learn a capability to identify precise boundaries with a relatively small labeled data in fine-tuning stage. The existing pre-training approach is short-level contrastive learning. It aims to learn better representation of individual shots, so it can easily capture the coherence or difference between shots. There are three strategies to sample positive pairs for contrastive learning: instance, temporal, and nearest neighbor. Let us consider 5 shots and talk about how to select positive pair in each method. Instance strategies use the same shot but is applied with a different augmentation policy. To further model the relation between shots, temporal scheme uses its neighbor shots with random sampling to make a positive pair. However, such random sampling may lead to false positive pairs. Inspired by this, nearest neighbor sampling is proposed to use the most visually similar shot among neighbor shots as a positive pair. This is effective in learning good representation of individual shots. However, we observe that it is not enough to learn contextual relations between shots. Let's see 2 examples. The first example contains a single scene with visually dissimilar shots, where shots highlighted in the same color look similar. In this example, both the shots are visually different in that they contain different characters. We expect such 2 different shots to be categorized in scene-level semantics of 2 characters talking on the phone. So the models need to maximize the intra-scene similarity. However, NM-based sampling pushes the representation of visually dissimilar shots in the same scene to be far from each other. This may lead to predict many short-level boundaries rather than scene-level boundaries. Those 2 different scenes, which contain visually similar shots highlighted in blue, where the same character appears in the same place. Here, we expect such 2 visually similar shots to be distinguishable, so models need to maximize inter-scene discrimination. However, NM-based sampling makes the visually similar shots from 2 different scenes be close. Thus, in this example, The model can think all shards belong to the same single scene, not different scenes. To maximize the intra-scene similarity and the inter-scene discrimination, we propose to identify a semantic transition moment as a pseudo-boundary. And we use it to design pretext tasks for learning contextual relation between shards across the semantic transition. In a nutshell, after identifying the pseudo-boundaries, we maximize the inter-scene discrimination by driving shards from two different pseudo-scenes to be similar, and maximize inter-scene similarity by encouraging shards in the same pseudo-scene to be similar. We compare possible pseudo-boundary candidates and select a moment where semantic change is maximum. Note that this process can be efficiently computed using dynamic time wiping technique, where we align intermediate shards either to the first shard or the last shard. Given the pseudo-boundaries and pseudo-scenes, we propose three boundary-aware pretext tasks. The first one is shard-scene matching, which makes the representations of a shard and its associated pseudo-scene similar to each other, but the representation of the shard and other pseudo-scenes dissimilar. The second one is contextual group matching. This measures the semantic coherence by deciding if the given two shards belong to the same pseudo-scene or not. These two pretext tasks are proposed to maximize the intra-scene similarity and to minimize the inter-scene similarity. The third one is pseudo-boundary prediction. This predicts whether the given shard is a pseudo-boundary or not. This pretext test gives the capability of identifying extension moment that semantic maximally changes. Finally, we additionally adapt masked shard model, which reconstructs the representation of masked shards based on their surrounding shards. Although it is not boundary-aware pretext task, it is helped to increase the inter-scene similarity. Experimental result, we summarize the contrast between shard-level pre-training method and our method. During the pre-training step, shard-level pre-training method takes a pair of two shards as an input and conducts shard-level contrast tasks, whereas our boundary-aware pre-training task takes the sequence of shards and perform boundary-aware pretext tasks. By this difference, shard-level pre-training runs simple individual shard representation, but a method runs relation between shards. In addition, shard-level pre-training method pre-trains a shard encoder only, but our method runs both the shard encoder and the contextual relation network. Thus, in only our method, the contextual relation network can be transferred to fine-tuning. These two main differences running CRN with boundary-aware pretext test and the transferability of CRN is really important for precise scene segmentation, which will be validated in our experiment. For the experiment, we first perform in-depth analysis, and we can observe four things. The first one is for the architecture of CRN, LSTM or transformer is more effective than MIP. This is because they are favorably designed to capture contextual relation between shards. Second, in-domain representation learning is very important. When you pre-train a model using only image-level labels or place information, it brings worse performance due to the domain gap. Third, while pre-training is itself effective, it turns out that boundary-aware pre-training is more effective than shard-level pre-training. This indicates the importance of learning contextual relation between shards by maximizing inter-scene similarity and inter-scene discrimination through pseudo-boundary discovery. Finally, pre-training and transferring the contextual relation network is also important, as it is in charge of modeling contextual relations between shards. As the next experiment, we investigate the impact of each pretext task. Here we can see each pretext task contributes to the performance improvement. We additionally visualize the similarity maps between shots when we include more pretext tasks. When the only MSM is used, as expected, cell clusterings are visible, but similarity around the boundaries are smoothed. This similarity around the boundaries are to be sharpened. This is thanks to the learning of capability capturing the semantic transitions. Then, with an additional CGM, the clusters are more clearly distinguishable through the learning coherence between shards. Finally, adding SSM makes the shards within the same cluster be more similar to each other by maximizing inter-scene similarity and inter-scene discrimination. Performance on MovieNet segmentation dataset is as follows. When you consider a method as an unsupervised method with only pre-training, our method shows competitive performance compared to the existing method. With fine-tuning, our method outperforms the previous state-of-the-art method SharpCore with a large margin. Thank you for your attention. If you are interested in using our models, please visit our GitHub.